Gravity is not a single force. It is a quiet conversation between mass and the fabric of spacetime, unfolding beneath every falling leaf and every orbiting star. But deep beneath that smooth pull, something stranger is happening. At the smallest scales, gravity begins to flicker. Rules that feel certain bend, and the universe reveals a mystery we are only beginning to understand. What happens when gravity becomes quantum? Before we drift deeper into this gentle night, if this calm journey brings you even a moment of peace or curiosity, I'm deeply grateful you're here. A soft like or a quiet tap on subscribe helps this small sanctuary of wonder continue glowing in the dark. Now, let us begin with the first quiet question. Part 1. The smooth gravity. We know. Gravity feels consistent, steady, like the invisible hands that keep your feet on the ground and planets bound to stars. General relativity describes this with elegance. Mass curves spacetime, and motion follows that curve. But this theory, as complete as it feels, is only half the story. Because when we look closer, far closer, the smooth fabric begins to tremble. For now, though, let's stay in the realm where gravity feels certain, where it shapes the orbits of moons and planets, controls the rise and flow of tides, and gently guides galaxies in their vast spiraling motion. You don't feel gravity tugging at you, and yet it is always there, a silent architect of your every movement. Even as you lie still, the force holding you to Earth stretches across 150 million kilometers of space, binding our world to the sun in a dance measured by light and time. Einstein once said that gravity is not a force in the traditional sense. There is no invisible string pulling you downward. Instead, space-time itself is curved by mass. The Earth presses into the fabric of the universe, and everything near it simply follows the shape that indentation creates. When you drop a stone, it falls not because gravity drags it, but because space-time slopes downward, guiding the path it must take. It moves the only way it can. This shift in understanding changed everything. Before Einstein, gravity was simply a pull described by Newton's elegant equations, consistent, predictable, but without deeper explanation. Einstein gave it a cause. Now the universal attraction felt by planets, bodies, even beams of light could be traced to geometry itself. Space is not a stage on which physics plays out. Space is a character. It bends, stretches, and curves, constantly changing with every mass and every motion. General relativity has been tested again and again. When stars pass behind distant galaxies, their light bends gracefully around massive clusters, creating arcs of brightness in the sky. Gravitational lensing. When pairs of black holes collide, they send ripples through spacetime, gravitational waves that observatories on Earth have now heard like gentle chimes from the farthest reaches of reality. These are confirmations that Einstein's view of gravity is not metaphor, but measurable truth. Even the ticking of time depends on gravity. High above Earth's surface, gravity weakens and clocks run slightly faster. Astronauts age a little more quickly than those who remain on the ground, fractions of a second gained against the pull of the planet. On Earth, valleys experience time a tiny bit slower than mountaintops. The deeper into a gravitational well you fall, the more time stretches and slips. Gravity and time are inseparable. This interplay is most visible in extreme places, around black holes, where gravity becomes a slow-motion trap. To an outside observer, anything falling into a black hole appears to freeze in time, never quite crossing the boundary between the outside universe and the darkness within. In truth, it continues, but time itself behaves differently there. The smooth equations of relativity describe this with perfect confidence. In the large-scale universe, gravity speaks clearly. But try to shrink the picture. If you zoom in on a star, then on a single atom inside that star, then further still on the particles inside those atoms, gravity's voice grows faint. It becomes subtle, too subtle. The smaller the scale, the weaker the gravitational influence becomes. until it begins to behave in ways the equations of relativity can no longer predict. Gravity works perfectly when describing planets, galaxies, clusters, and black holes. But the quantum world, the realm of the very small, plays by different rules. A particle doesn't have one position. It has a cloud of possible positions. It doesn't move on a smooth curve, but exists in probabilities. Its forces are exchanged by particles that pop in and out of existence. And if gravity is a fundamental part of nature, it should behave the same way. But it doesn't. At least, not with the laws we currently understand. This is where the smoothness of spacetime becomes a puzzle. In general relativity, spacetime is infinitely divisible. No smallest piece, no granularity. It is a perfect sheet that can be bent into any shape. But in quantum physics, nothing can be infinitely smooth. At small scales, uncertainty reigns. Space itself may need to be granular, built from discrete building blocks too tiny to perceive. As you breathe gently in this moment, your body sits atop a planet with a space-warping mass. Your atoms hold together through quantum forces that differ from what gravity describes. And yet, both frameworks apply to you at once, two different rulebooks governing the same reality. For now, they coexist by ignoring each other's domains, quantum physics at the tiny scale, general relativity everywhere else. But nature itself does not split apart so easily. Reality must have one framework, one rule, one truth. Our job is to find it. Consider how strange our understanding still is. Gravity shapes galaxies, but we cannot fully describe how it interacts with a single particle. The motion of entire worlds is easier to understand than the force holding the smallest grain of dust to the floor. This gap is unsettling, not because it suggests ignorance, but because bridging it could reveal something profound. Perhaps time itself is not smooth. Perhaps the very concept of distance fails at tiny scales. Perhaps the space-time fabric Einstein described tears and reforms under quantum pressure, hiding secrets older than the universe itself. Yet, despite these unknowns, the gravity we know remains precise and consistent. It guides satellites around Earth with flawless accuracy. It predicts how planets move centuries into the future. It shapes the cosmic web that stretches across billions of light years, connecting clusters of galaxies with dark filaments of matter. It is the quiet engine of structure. Even with its mysteries, gravity is why you feel grounded at night as you drift towards sleep. It is why the moon does not drift away into the abyss. It is why stars ignite in clouds of gas collapsing under their own weight. Life exists because gravity gathers matter, holds heat, and balances motion. At the largest scales, gravity is the storyteller of the universe. It creates beginnings and endings, forming stars, collapsing them, shaping black holes that anchor galaxies and sculpt time. It governs destinies written in motion and mass. But the story is incomplete. We know gravity can bend starlight, but can it bend probability? We know time slows under its influence, but does time itself have quantum pieces that gravity must interact with? Each question invites another. Each answer deepens the mystery. And somewhere at the smallest imaginable scale, gravity must become quantum, a unified truth waiting to be discovered. As we drift deeper into this exploration, one quiet question remains. If gravity is so smooth and certain at the vastest scales, what happens when we look into the very smallest ones, where certainty disappears? In the next chapter, we take the first step into that smaller, stranger world, where gravity no longer behaves like the calm guide we know, and the laws of physics begin to shift beneath our feet. Part 2. Quantum worlds don't like smoothness. In the quantum realm, nothing is continuous or certain. Motion becomes probability. Location becomes a blur. Here, particles don't follow smooth curves. They leap, scatter, and exist everywhere and nowhere. And gravity, which relies on smoothness, begins to fail. This is where the universe asks us to rethink everything we know. If the world behaved the way quantum physics insists that it does, your hand would never truly rest on your pillow. The atoms in your skin would constantly exchange energy with the air, electrons vibrating and shifting in invisible dances. Every time you blink, countless particles appear, and vanish in the empty space before you. Nothing stays still. Nothing is precise. The quantum world is restless. The smallest scales, the concept of a path, a line traced through time, is replaced by uncertainty. A particle can only be described by a cloud of potential positions. We call this a wave function. It doesn't tell us where a particle is. It tells us where it might be, where it might appear if the universe decides to show its hand. And when we try to measure the particle, the wave collapses. Certainty appears only in the moment we attempt to observe it. The rest of the time, existence is a haze of probabilities, reality holding its breath. This principle lies at the heart of quantum mechanics. The more precisely we try to know one property, like position, the less precisely we can know another, like momentum. Heisenberg's uncertainty principle isn't a limitation of our tools. It's a rule of existence. Even energy fluctuates, refusing to remain constant. In the vacuum of space, unseen particles flicker into being, exchanging forces and disappearing again. They are called virtual particles, though there is nothing imaginary about their effects. Their jittering presence influences everything from chemical bonds to the structure of atoms themselves. In this world, probability is the foundation, not certainty. Gravity, on the other hand, relies on certainty. General relativity assumes that spacetime curves smoothly. No flickers, no jumps, no uncertainty. A planet moves along geodesics, gentle curved paths, because the geometry itself is predictable. But if you were small enough to fall into the domain of quantum rules, the path would dissolve. Imagine the fabric of spacetime not as a smooth canvas, but as a rough mosaic, tiny tiles of geometry shifting in unpredictable bursts. Motion across such a surface would not be graceful. It would be jagged, uncertain, fragmented. A particle trying to follow a curve might instead be forced to hop, one discrete point to another, like a skipping stone across the smallest scales of existence. This conflict is one of the most profound in physics. Gravity demands smooth geometry. Quantum mechanics demands uncertainty. Both cannot be fully correct in the same regime, yet both shape the universe you live in. Zoom out, and planets move in perfect arcs. Zoom in, and particles jitter with no clear trajectory. Somewhere between those extremes, the two realities must converge. We simply haven't found where yet. Night after night, as you sleep, your brain runs billions of quantum events to help your neurons fire. At the same moment, gravity anchors your body firmly to Earth. Two competing rule sets working together to let you dream. Science has learned to treat them separately because combining them remains the greatest unsolved equation in physics. Every major leap in understanding the universe has come from unifying what once seemed separate. Electricity and magnetism became electromagnetism. Space and time became space-time. Mass and energy became two forms of the same essence. Now the universe offers one final unification challenge. Gravity and quantum mechanics must one day speak the same language, but for now, they argue. Consider a black hole again. At its edges, the event horizon, general relativity says space-time curves infinitely, but quantum mechanics says infinities cannot exist. A singularity is a place where both theories fail to describe the same reality. The closer we try to get to the center, the stronger the disagreement becomes. Information about matter falling into a black hole should be lost forever. Gravity smiles and nods at this idea. But quantum physics refuses. It states that information cannot vanish ever. And thus begins the black hole information paradox, a disagreement that has lasted decades, weaving through the work of Stephen Hawking and countless physicists since. This paradox isn't academic. It's a sign, a beacon pointing to a deeper truth, one we have not unlocked. Because if two foundational theories collide, the universe must be hiding a third framework beneath them, uniting them into one. Even distance itself becomes uncertain in the quantum view. Space can stretch and contract with no clear boundary. The smallest measurable distances are not smooth lines, but fuzzy regions where space-time may fray like loose thread. At these scales, general relativity cannot guide us. Gravity becomes silent. To explore this world, we must rely not on mass or curvature, but on frequency. particles exchanging messengers of invisible force. The quantum realm explains the strong force, the weak force, electromagnetism, with particles, gluons, bosons, photons. They leap between objects, linking them in silent communications. But where is gravity's messenger? Physicists believe that if gravity is quantum, it must have a particle too, the graviton, a hypothetical quantum of gravitational interaction. It would be massless, it would move at the speed of light, and it would be impossibly hard to detect. Just one graviton passing through your finger would require a detector the size of Jupiter, operating for longer than the age of the universe, and even then, success is not guaranteed. So gravity remains ghost-like, quiet, and hard to touch. Quantum mechanics also refuses to allow anything to remain rigid, not even space-time itself. At the smallest scale, the Planck length, the geometry of the universe is expected to twist and swarm in unpredictable fluctuations. Space and time behave like a liquid foaming and collapsing. And in that turbulent chaos, gravity must also become quantum, though we have never seen it do so. As you breathe now, the quantum world continues its invisible dance inside every atom of your body. It shapes the chemistry that keeps your heart beating. It allows electrons to tunnel through barriers, enabling life to exist at all. You are quantum, you are curved space-time, you are both. Which means somewhere inside you, the worlds must meet. They already do, quietly, invisibly. But our theories have not yet met them there. This conflict is not a flaw in nature. It is a flaw in our understanding. A sign that beneath uncertainty and curvature lies something deeper, a hidden symmetry, a new framework waiting for its discovery. Quantum mechanics has shown us that the universe is stranger than we ever imagined, and gravity has shown us that it is more connected than we ever believed. Now the next question whispers softly, if the quantum world refuses smoothness, what happens to gravity at the very limit of the small, where space-time collapses into pure uncertainty? In the next chapter, we take our first step toward that boundary, where distance itself dissolves into the mysterious Planck scale, and the laws we trust fade into silence. Part 3. The Hidden Scale. Where physics disagrees. If we zoom in past atoms, past their nuclei, past quarks themselves, we approach a boundary called the Planck length, 1.6 or 1035 meters. At that scale, gravity and quantum mechanics clash. Space-time ripples like a sea in a storm. And our best theories simply stop agreeing. To give this scale meaning, imagine shrinking the entire observable universe, every galaxy, every star, every atom, down to the size of a single grain of sand. On that scale, the Planck length would still be a tiny fraction of that grain. It is so small that if a proton were stretched to the size of the Earth, a Planck-length object would be smaller than a single atom resting on its surface. It is not just beyond our microscopes, it is beyond imagination, and yet, this imperceptibly small scale is where the universe may reveal its deepest truth. Here is what makes the Planck length so important. It is the point at which quantum mechanics and general relativity predict entirely different things. When we describe gravity at large scales, stars, planets, galaxies, Einstein's smooth space-time works perfectly. When we describe the tiny, electrons, quarks, photons, quantum mechanics, reigns with astonishing accuracy. But below the Planck length, the universe refuses to pick a side. Einstein says space-time is continuous, a perfect curve. Quantum mechanics says everything is granular, discrete, unpredictable. Both have been proven right over and over. But when forced to occupy the same scale, they fall apart. Physicist John Wheeler once suggested that at this depth, space-time is no longer a fabric, it is a foam. Think of waves crashing against one another in a turbulent ocean, peaks rising and collapsing, whirlpools forming and dissolving. That is the Planck scale. Space flickering between existence and disappearance, time stuttering between moments, nothing stable enough to be called a location, nothing smooth enough to be called a curve. Our ruler breaks, our clocks fail, our words become metaphors, even distance and duration lose meaning. The Planck length is not just a size, it is a border, a threshold, a horizon across which our current mathematics cannot safely travel. This limit emerges from combining three of nature's most fundamental constants: the speed of light, the gravitational constant, Planck's constant. Together, they define a smallest meaningful unit of space. Below that, space may not be space at all. It may be nothing, or something entirely new. This boundary also comes with a sister measurement, the Planck time, the smallest interval that can be said to exist. 1 Planck time is how long light needs to travel 1 Planck length, about 5:39·10·44 seconds. Shorter than that, time may lose its direction. Before that time passed after the Big Bang, the universe may not have had a before and after. Below the Planck scale, the universe doesn't just get smaller, it gets undefined. To probe this realm, physicists try to increase our particle smashing power. The higher the energy, the smaller the structures we can resolve. But there is a trap concealed in that idea. Pack too much energy into too tiny a region, and space-time collapses inward. You create a microscopic black hole. Your experiment disappears behind an event horizon. Even nature protects this scale from being directly observed. This is why many scientists believe the Planck scale represents not a technological limitation, but a fundamental limit written into reality itself. It is where the universe draws a curtain over the backstage mechanisms of existence. The structure of space-time here is unknown, yet theories whisper possibilities. Some physicists propose that space is quantized, a mosaic of discrete grains like pixels on a screen. But unlike a screen, the pixelation is fluid, forever agitated by uncertainty. This view forms the seed of loop quantum gravity, which envisions space woven from tiny loops of geometry. Each loop is a quantum of area, no smaller shapes allowed. Others lean into string theory, where every particle is a vibrating string, smaller than anything we can see. That picture, the Planck scale, is the length of the strings themselves, the smallest thread of reality's tapestry. Some imagine extra dimensions curled tightly at that size, hidden directions that gravity may spread into, weakening it for us at larger scales. That would explain why gravity is the faintest of all forces, why lifting your hand defeats an entire planet's gravitational pull. And there are even bolder ideas. That space-time at the Planck scale is not a place but information. That gravity may be nothing more than a consequence of quantum entanglement, tiny threads of shared state weaving reality into a connected whole. Each theory points to the same truth. The universe may be built upon something deeper than space and time. Still, we lack proof. Every attempt to calculate gravity's quantum behavior ends with infinities, numbers the universe itself cannot allow. When we try to simulate space-time curvature at those small scales, our equations explode into impossible results. Infinities signal failure. Failure signals ignorance. Ignorance signals opportunity. Perhaps the universe is telling us that our understanding is incomplete, not wrong, but unfinished. We stand on the boundary between two kingdoms of physics, each correct in its domain but incompatible on common ground. And somewhere in the Planck scale darkness lies the peace treaty that will unite them. Look around your room. Every object is held together by quantum forces. Every motion in orbit is guided by gravity. You are living evidence that the two worlds meet harmoniously. But our description has not yet caught up to nature's perfection. We are missing the key. And so, physicists push forward. They listen to black holes merging billions of light years away. They measure gravitational waves humming like distant music. They map the cosmic microwave background to detect tiny patterns echoing from the first instance of existence. In every extreme, the Planck scale leaves its fingerprints. One day, we may decipher those patterns. One day, the riddle may open. For now, the Planck length stands as physics' quietest frontier, a reminder that even after centuries of discovery, the universe still holds secrets deeper than imagination. As we drift farther into this exploration, toward places where energy and geometry collapse into each other, one question guides us gently onward. If gravity falters at the Planck scale, can we discover a new particle or principle that ties the large and the small into a single seamless truth. In the next chapter, we follow that possibility into the strange idea that gravity itself might come in tiny packets carried by a particle we have never seen, the elusive graviton. Part 4. Quantum foam, a chaotic foundation. Physicist John Wheeler once described spacetime at the tiniest scales as quantum foam, a restless ocean of microscopic collapses, expansions, twists, and tunnels. A place where the idea of a straight line has no meaning. Each fluctuation is brief, yet together they may weave the very texture of reality. Imagine the calm surface of the ocean at night, smooth, dark, undisturbed. That is spacetime as we experience it, predictable, continuous, obedient to the rules gravity has set. But now imagine sinking beneath that calm surface. The deeper you go, the more the water churns. Bubbles rise, currents twist, gaps appear and close. Pressure and unpredictability replace stillness. That is the quantum truth beneath the illusion of smooth spacetime. The Planck scale is the universe's deepest ocean floor, where geometry becomes wild. In everyday physics, we expect space to hold still, a fixed stage upon which everything else performs. But at this unimaginable depth, space behaves almost like a living organism, constantly reshaping itself. Tiny pockets of space expand outward before being consumed by neighboring compressions. Loops of geometry rise and pop. Wormholes, infinitesimal shortcuts between points, appear for brief flashes of time before dissolving into nothing. This is quantum foam, a roiling storm of existence. Nothing here is deterministic. Nothing is stable. There is no forward or backward. Time itself stretches and snaps like a thread caught in wind. In these flickering moments, the boundaries between here and not here become indistinguishable. Space does not maintain distance. Time does not maintain order. Reality does not maintain form. Where you expect silence, there is turbulence. Where you expect structure, there is foam. Where you expect laws, there is possibility. Wheeler's vision was bold, an attempt to describe what happens where gravity and quantum mechanics collide. And what he found was that at the smallest scales, spacetime is fundamentally uncertain. The foam is not chaos without rules, but chaos that obeys rules we do not yet understand. Even nothingness is busy in a perfect vacuum far from stars and galaxies. Space is not empty. It boils with energy, pairs of particles constantly appearing and annihilating each other. According to quantum field theory, these fluctuations are unavoidable. Every field in nature, electric, magnetic, even gravitational, trembles with activity. Like waves too small to see, but powerful enough to change the universe. Physicists call this zero-point energy, the minimum energy a physical system must always have. Even when a system is cooled to absolute zero, motion remains. Life remains. The universe refuses perfect stillness, and these invisible fluctuations have real consequences. They change how particles move. They alter the force between atoms. They even reshape the vacuum itself. It is as if the foundation of reality is built on restless movement, endless, ceaseless vibration. The calmness we trust is a quiet average of this underlying storm. Here is the mystery. If quantum foam is constantly stretching and collapsing spacetime, why do we not see that turbulence in our everyday world? The answer is scale. Like grains in a piece of glass, the microscopic structure of spacetime is hidden by the smoothness of the macroscopic surface. The foam is so tiny that its wildness cancels out when billions upon billions of fluctuations sum together. The chaos is averaged into calm. Yet the foam leaves clues, subtle fingerprints detectable in extreme environments. Near a black hole's event horizon, for instance, the calm geometry of spacetime is tested against the quantum vacuum. Stephen Hawking realized that the foam bubbling near the surface of a black hole produces radiation, particles that escape into space. We now call it Hawking radiation, one of the most astounding predictions in physics. The evaporation of black holes is a whisper from the quantum foam. Even the expansion of the universe may trace back to its chaotic origin. In the first instant after the Big Bang, spacetime may have been nothing but foam, and tiny. Fluctuations stretched to cosmic scale became the seeds of galaxies. The random flicker of quantum foam determined where stars would one day burn. A microscopic storm, a macroscopic universe, one foundational truth. If we could freeze the foam in time, hold its snapshot still, we might see the birth of geometry itself. Wheeler suggested that spacetime is not fundamental. Instead, it emerges from deeper quantum events. Tiny networks of connectivity may give rise to distance and dimension. When enough of these networks align, space appears smooth. When they fragment, time and causality distort. Space becomes a product of information. Time becomes a product of change. Gravity becomes a product of structure. This idea reshapes everything we know. Because if the foam builds reality moment by moment, then existence is not static. It is continuously generated, like a film playing frame by frame. The present is not a solid thing, but a process, a continuous emergence. Some researchers believe that the universe may not be a place at all, but a computation. Each Planck-sized bubble acting as a tiny bit of logic, processing reality in discrete steps. In that view, the foam is both the hardware and the code, a universe that calculates itself. Others argue that quantum foam is evidence of hidden dimensions, tiny curled spaces too small for particles to reach. Foam may be the flicker of these dimensions coming in and out of contact with ours. If true, the secrets of gravity could be written just outside our perception. And there are more daring theories still. Perhaps wormholes in the foam connect distant regions of spacetime, stitching the universe together. Perhaps entanglement between the foam's building blocks gives rise to the smooth surface above it. Perhaps reality is relational, that only interactions define what exists. Every possibility is a doorway. Every doorway leads to a deeper question. Why does small-scale chaos create large-scale order? How does turbulence shape stability? How does universality emerge from randomness? Quantum foam suggests that uncertainty is not a flaw in physics. It is the origin of physics. It provides the motion needed for symmetry to break, for laws to form, for time to tick, and for space to stretch. It is the heartbeat beneath existence. As you rest tonight, the world feels stable beneath you. But beneath every grain of sand, inside every atom of your body, space-time whispers and churns with limitless complexity. In that tiny ocean, the first notes of gravity may be played by a particle we have not yet seen, a messenger of curved geometry, a quantum of attraction, the graviton. If quantum foam is truly the stage upon which reality is written, then the graviton may be the first actor we are meant to meet. And if we can detect it, if we can listen closely enough to hear its faint presence, gravity itself may finally reveal its quantum nature. So we continue our journey downward, deeper into the unknown, toward the particle that might connect these scales. In the next part, we follow the search for this invisible messenger to discover whether gravity too comes in tiny, trembling units of existence. Part 5. Gravitons. If gravity had a particle. Every known force has a particle that carries it, photons for light, gluons for the strong force. If gravity is also quantum, it too must have a carrier, a graviton, a particle that has never been seen nor detected, yet might exist in unimaginable numbers all around us, guiding every fall, every orbit, and every heartbeat. If the universe truly speaks in particles, then a graviton would be the quietest word in that cosmic language. It would have no charge, no mass that we could weigh, and no color or flavor or spin that we could easily witness. It would simply move, silently and relentlessly, weaving together the shape of space-time itself. Every attraction, leaf to earth, moon to planet, star to galaxy, would be the sum of countless invisible exchanges. Right now, as you rest, trillions of gravitons might be passing through your body every second, and yet they leave no trace you can feel. Gravity is the most familiar force and the most elusive. We know its effects with absolute certainty, but its quantum messenger remains a ghost. Why is it so hard to find? Because gravitons would interact so weakly with matter that they might as well be shadows of particles, present in theory, undetectable in practice. To reveal one, scientists would need detectors larger than planets, with sensitivity beyond imagination. Even our most advanced gravitational wave observatories, vast instruments capable of detecting distortions smaller than 1,000th the width of a proton, listen to gravity only when it screams, not when it whispers. But gravitons would whisper only. To understand their role, it helps to recall how other forces behave. Photons, for example, are carriers of electromagnetic interaction. When two electrons repel each other, they exchange virtual photons in rapid bursts of quantum communication. A single beam of light can flood your eyes with millions of photons in a blink, and those photons can be counted, measured, stored. Imagine trying to do the same with gravity. If we attempted to detect a graviton from an orbiting planet, the signal would be dwarfed by background noise. It is as if gravity is whispering across the room while 1,000 storms howl around us. Every experiment we attempt is drowned out before the first attempt begins. So why believe in gravitons at all? Because if gravity is to be unified with the quantum world, it must behave like the other fundamental forces, transmitted not continuously, but in discrete units. In that picture, gravitons would be the smallest possible step of curvature in spacetime. They would be the quantum pixels that shape the geometry around mass. Without them, we cannot fully explain how particles with mass feel gravity, or how gravitational influence travels through the universe at the speed of light. The math suggests they must exist. Nature simply has not yet allowed us to see one. Let's imagine, gently, what a graviton might be like. It would travel forever unless it meets a particle with enough gravitational sensitivity to absorb it. It would pass through stars effortlessly, through planets, through your body, through mountains and oceans. Even black holes might not trap them completely. Quantum theory predicts that the horizon of a black hole might shimmer with gravitons as information escapes. To detect one graviton, scientists estimate we would need a detector made of neutron star-like matter, held at absolute zero, isolated from every vibration in the universe. And even then, detection might require waiting longer than the current age of the cosmos. The universe has placed gravitons in a realm beyond our touch. But absence is not non-existence. Even before we had microscopes, atoms shaped the world. Before we knew light could behave as particles, photons painted the heavens. Belief is not what defines a particle. Evidence may arrive slowly in physics, trailing behind theory like light traveling from a distant star. The discovery of the graviton may simply be waiting for a more advanced age, one where technology can catch up to curiosity. There is another possibility, one that bends the imagination even further. It may be that gravitons are not particles in space, but the result of something deeper than space. Some modern theories propose that gravity is not a force at all, but an emergent phenomenon, an illusion arising from quantum entanglement. In this picture, spacetime forms because particles share information. If those invisible connections break or rearrange, gravity changes accordingly. Here, gravitons would not be fundamental building blocks, but waves in a sea of quantum relationships. A universe where gravity is not pushed but remembered. This leads to a haunting thought: gravity might be the shadow of the universe thinking. Other theories take a different path, suggesting that gravitons are the manifestation of tiny vibrating strings in extra hidden dimensions. If these strings loop freely, they create particles with properties matching what we expect of gravitons. In that view, gravity seems weak because its strings vibrate in dimensions we cannot see, leaking influence away from our visible world. Two visions of reality, both beautiful, both unconfirmed. Yet, even without direct detection, the search for gravitons guides us toward unification. If we could understand how gravity becomes quantum, we might finally merge the smooth curvature of spacetime with the sharp uncertainties of the atomic world. We might discover the missing framework that ties every known law of physics together into one equation. Every major breakthrough in science has come from recognizing what is unseen. Electric fields existed before we could measure them. Neutrinos passed through Earth for centuries before anyone believed in them. Dark matter shapes galaxies while hiding completely from our eyes. Gravitons may be the next truth to emerge from silence. Consider this: a graviton would ripple spacetime, tiny and gentle, like a feather brushing the skin of the universe. If we could ever listen closely enough, we might hear the smallest tremor in the structure of existence, gravity speaking in its native tongue, one particle, one message, one unification. So we keep searching. We build detectors that stretch kilometers across, mirrors polished to perfection, lasers that measure distances smaller than atoms. We analyze collisions of black holes billions of light years away, hoping one day to resolve their quantum notes. We push theory toward the places mathematics grows thin, hoping to find a bridge across the boundaries we do not yet understand. The graviton, whether real or symbolic for now, represents hope that the universe can be explained using one shared truth. As you breathe in this moment, the world feels calm, steady, held in place by an invisible order. Gravity keeps your body grounded, but below that tranquility lies a hidden dance, possibly choreographed by trillions of unseen particles passing silently through everything you know. If gravitons are real, they are everywhere. If gravitons are not, something equally mysterious takes their place. Either way, the message is the same. There are secrets in motion. And as we continue to drift deeper into this quiet, unfolding mystery, another question comes to light. What if gravity shapes not only the motion of matter, but the structure of space itself, woven from something even finer than particles? In the next part, we explore that possibility, entering a universe made not of points and trajectories, but of vibrating strings and invisible dimensions hidden just beyond our perception. Part 6. When black holes shrink into the tiny black. Holes are shaped by gravity, yet powered by quantum behavior. At their cores, space and time collapse into a single point, a singularity. Some physicists believe that inside such a point lies the ultimate quantum gravitational mystery, a boundary between our laws of physics and a deeper truth waiting to emerge. A black hole seems like the simplest object in the universe. It has only 3 measurable properties: mass, spin, and electric charge. It has no surface, no solid body. It is emptiness, gravity made manifest. And yet within that apparent simplicity hides the most extreme terrain known to physics. Imagine falling toward a black hole. From afar, its shape looks like a perfect sphere of darkness, silent, absorbing light itself. But as you approach the event horizon, the invisible boundary beyond which escape becomes impossible, time begins to stretch. Clocks slow, signals fade, space bends inward. Outside, observers would see you freeze at the horizon, your image stretched into red light, fading into nothing. But you, continuing downward, would feel nothing unusual as you cross into the region where time converges with gravity's hunger. Gravity does not shout, it whispers. Deeper inside, the fabric of the universe becomes impossibly steep. Space pulls inward with such ferocity that every path leads only one way, toward the center, toward the singularity. And there, physics as we know it unravels. General relativity insists that the singularity is infinitely small and infinitely dense, a point containing all the mass of the collapsed star. Quantum mechanics rejects infinities entirely. It claims that something must stop the collapse, that there must be a smallest unit of space, a minimum volume where reality refuses to compress further. Two towering theories stare into the same darkness, but describe different truths. This conflict, hidden from sight inside every black hole, is a signal that spacetime has a secret deeper than either theory alone can tell. What if singularities are not points at all? Some physicists believe that once matter shrinks to the Planck scale, quantum pressure pushes back against gravity. The collapse slows. The infinite curve of spacetime becomes finite. The singularity dissolves into something else, something we have no name for yet. Others think that black holes contain bridges, wormholes, leading to distant regions of space or even other universes. In that view, the singularity is an entrance, not an end. Gravity folds the cosmos into new geometries, stitching faraway places together. And then there is the possibility that a singularity is a star's final transformation, its mass converted into pure quantum information, a concentrated memory of everything it once was. The black hole becomes a vault. This leads us to one of the deepest paradoxes in physics. Information, once swallowed by a black hole, seems lost forever. But quantum mechanics refuses to allow information to vanish. Every scattering, every decay, every particle interaction must keep a record, however faint. The universe is a historian. It never forgets. Stephen Hawking, studying black holes, realized that they emit faint radiation due to quantum fluctuations near the horizon. Over unimaginable spans of time, black holes could evaporate completely. But if the black hole disappears, where does the information go? Does it radiate back out, encoded in light too subtle to decode? Is it preserved in a remnant smaller than atoms? Or does gravity hide information in new dimensions we cannot observe? The black hole information paradox is the clash point where gravity's geometric order meets quantum unpredictability. It demands a theory that combines the two, one that describes atoms and galaxies with a single language. Black holes are not cosmic graveyards, they are laboratories. Their edges, the event horizons, are among the most fascinating surfaces in existence. Area, not volume, determines a black hole's entropy, its internal disorder. This discovery led physicist Jacob Bekenstein, and later Hawking, to realize that a black hole's information content scales with its surface. That finding inspired the holographic principle, the idea that our universe itself may be a projection from a distant boundary, a cosmos encoded on a surface with depth as an illusion. Black holes are the proof that such thoughts could be real. Imagine a star heavier than our sun collapsing under its own weight. It shrinks past any stable form, past atoms, past nuclear matter, past the existence of protons and quarks. Gravity compresses it to a point where the quantum structure of spacetime must reveal itself. A black hole is not only dense matter, it is the gateway to the Planck realm. At that scale, every assumption fails. Distance becomes uncertain. Time flickers into randomness. Curvature reaches beyond the calculable. Black holes show us where new physics must be found. They even demonstrate the tension between locality and connectedness. Quantum entanglement suggests that particles remain linked regardless of distance. Meanwhile, gravity demands that information falls inward and vanishes. To reconcile these ideas, some scientists propose that spacetime itself emerges from entanglement, black holes being the ultimate knots in that invisible web. Another astonishing thought: black holes may not collapse into singularities at all. Instead, they could bounce. Some theories propose that the shrinking core could reach Planck density and then explode outward, not as fire, but as new spacetime. A black hole could transform into a white hole, spitting matter and information into the future. A star's death becomes the birth of structure somewhere or somewhen else. Where would that explosion lead? To another region of our universe, or into a separate one entirely? Could our own universe have been born from such a bounce? A cosmic memory of a black hole in a parent universe? This is speculation, yes. But so is relativity, once. So is quantum theory. So were black holes themselves. The universe often hints at truths long before our equations catch up. As you lie here, gravity gently holds you to Earth. Yet far away, black holes test gravity to its breaking point. Their existence proves that general relativity is incomplete. Their mystery proves that quantum mechanics is incomplete. They are not puzzles to solve. They are maps. A black hole contains the key to unifying physics, hidden at a center we cannot reach. Its event horizon is the veil between what we know and what remains unsolved. Every signal that emerges, every gravitational wave, every flicker of radiation carries a clue. Each collision of black holes is a cosmic experiment, billions of years in the making, delivering data to our detectors like whispers from the universe's edge. Someday, the singularity may not be a mystery. It may be a doorway. As we continue this quiet descent into the quantum nature of gravity, one question emerges like a star behind a veil. why is gravity so weak if it binds the universe so strongly? In the next part, we explore this strange imbalance, discovering whether gravity is truly faint or simply spread across worlds we cannot yet see. Part 7. Why gravity is so surprisingly weak. Lift your hand. You are defying an entire planet's gravitational pull with almost no effort. Compared to the other forces of nature, gravity is incredibly faint. Some theories say it may leak into hidden dimensions, its strength spread thin across realities we cannot see. It is a strange thought. We experience gravity constantly. It keeps oceans anchored to Earth. It shapes the orbits of planets. It holds galaxies together against the spreading tide of cosmic expansion. And yet, when measured against the other fundamental forces, it is almost non-existent. The electromagnetic force, the strong nuclear force, even the weak force, all are vastly more powerful. If you bring two protons close together, their electromagnetic repulsion is about 1,036 times stronger than gravity's pull. That is a number so large it no longer feels like a number, it feels like a message. Gravity isn't just weaker. Gravity is almost not there at all. So why does the universe feel dominated by gravity? Because the other forces cancel out. Positive and negative electrical charges neutralize each other. Nuclear forces operate only within the tiny heart of atoms. But gravity cannot cancel, it only attracts. Every atom, every star, every galaxy adds its mass to the total pull. And across cosmic distances, that gentle attraction becomes the architect of structure. But the question remains, why is gravity so weak at the scale of everyday life? One idea is that gravity's strength is diluted, spread into dimensions beyond the familiar three of space and one of time. In this picture, while electromagnetic and nuclear forces are confined to a four-dimensional sheet, our observable universe, gravity may roam through a larger arena. It may flow outward into hidden dimensions, like water escaping through cracks. To us, trapped on the surface, gravity feels like a slow echo of a much stronger force. This concept arises naturally in string theory, where the universe may have extra curled-up dimensions too tiny for us to see. If gravitons, the hypothetical particles of gravity, can slip into those dimensions, their influence in our world would appear faint. What seems weak may simply be spread thin. Another idea, gravity might not be fundamental at all. Perhaps it emerges from the collective behavior of countless quantum interactions. Like temperature arising from the motion of atoms, gravity could arise from hidden information patterns. In this view, the weakness of gravity may be the signature of a deep relational structure, one that does not push or pull, but connects. This leads to an almost poetic possibility. Gravity is not a force. Gravity is the universe holding itself together. Even Einstein's perspective hints at this. He did not describe gravity as a push or pull, but as the bending of spacetime. Mass tells space how to curve. Space tells matter how to move. No force, just geometry. But geometry should not be weak. It should be universal. It should apply everywhere, equally. So the question becomes sharper. If gravity is geometry, what makes its curves so gentle? One clue comes from the smallest particles we know. Quantum mechanics tells us that everything is fuzzy, positions blur, energies fluctuate, particles constantly exchange virtual messengers of force, but gravity responds to mass and energy. And individual particles have very little of either. Their gravitational fields barely ripple spacetime at all. Imagine trying to bend a steel beam using a single grain of sand. The grain pushes, but the beam barely notices. Only when billions upon billions of particles gather into planets, stars, or galaxies does gravity's effect reveal itself. On the quantum stage, gravity is too subtle. On the cosmic stage, gravity is the star. Another clue lies in the coupling constants, the fundamental numbers that determine each force's strength. They are not the result of deep principles we fully grasp. They are measured, learned from nature's behavior. Why the strong force is strong and gravity is weak may simply reflect choices the universe made early in its history, choices we are still trying to understand. Perhaps the most compelling reason gravity feels weak is that we observe it incorrectly. Gravity acts not on charge, not on the quantum spin of particles, but on energy itself. And energy is conserved. It flows freely. It does not cluster into opposites that erase each other. So while electromagnetic forces cancel inside your body, the mass energy in your atoms adds up. That additive nature means gravity scales with size. The larger the system, the more gravity dominates. A proton feels almost no gravity, but a galaxy feels nothing else. Even the cosmos itself struggles with gravity's weakness. Dark energy pushes galaxies apart, slowly overwhelming their gravitational bonds. The universe may one day expand so rapidly that gravity can no longer form new stars. Weakness becomes loss. Distance becomes destiny. Yet weakness is not failure. Gravity shapes time. It sculpts the paths of photons. It controls the life cycles of stars. Even a faint whisper, repeated for billions of years, reshapes the universe. Imagine lifting your hand again. You are stronger than an entire planet, temporarily. But gravity never stops pulling, never stops gathering. It wins in the end. On the largest scales, gravity is the author of large-scale structure. It draws matter from chaos into spirals and spheres. Without gravity's gentle weakness, the universe would not be calm enough for galaxies to settle, stars to ignite, planets to orbit, or life to emerge. Weakness becomes the opportunity for balance. Balance becomes the possibility of existence. So the mystery remains, not as a flaw, but as an invitation. What lies beyond our senses? Where do gravitons hide? Where does the force of geometry truly live? Perhaps gravity is the one force that still refuses to reveal its true nature. It hides its quantum heart behind the smooth curves of spacetime. It softens itself so life can form between the cosmic storms. It speaks quietly so that deeper truths can be heard. Every night as you dream, Earth's soft gravity keeps you grounded, but somewhere far beyond, in the darkest corners of space, black holes stretch gravity to its crashing limit. There, its faintness becomes overwhelming strength. Its whisper becomes a roar. Weak here, powerful there, beautiful everywhere. As we drift further into this journey toward theories that try to harmonize the large and the small, another question guides us forward. If gravity is not the universe's final word, what deeper structure shapes everything beneath? In the next part, we turn to one of the boldest answers scientists have ever imagined, a universe built not from points, but from vibrating strings singing the music of reality. Part 8. String Theory's Gentle Vibrations. String theory suggests that every particle is a tiny vibrating string, and gravity emerges when certain strings loop freely. In this idea, the universe is music, and gravity is its deepest bass note. If true, quantum gravity isn't a correction, it is the foundation. Picture the smallest thing you can imagine, a grain of sand. Then go smaller, a speck of dust floating in sunlight. Smaller still, an atom, too tiny to see even with our most powerful optical instruments. We dive deeper, to electrons orbiting the nucleus. We keep going, to quarks inside protons and neutrons. And then we reach a question. Does nature stop here? String theory says no. Instead of points, with no size, it imagines that the true building blocks of matter are tiny loops or strands, like miniature rubber bands, vibrating in more dimensions than we can perceive. Their vibration determines what particle they appear to be. A different frequency, a different twist, a different shape, and the same string becomes an electron or a photon or a quark. Particles are not objects. Particles are melodies. The universe, in this view, behaves like an enormous instrument. Its physical laws the result of strings resonating in perfect mathematical harmony. Every possible note exists, but only certain ones play long enough and strong enough to form matter, energy, and space-time itself, even gravity. Unlike strings with ends that anchor to our familiar dimensions, some strings may form closed loops. These loops have no boundaries, no start or finish. They slip between dimensions freely, and their vibration corresponds to a particle with no mass, the graviton, a gravity-carrying string, a loop stitched into the geometry of everything. If that is true, then the weakness of gravity might be explained by its freedom. While other strings cling to the four-dimensional surface of our world, graviton loops wander into hidden directions. Their influence spreads thin, making gravity faint where we exist, yet powerful when viewed across the full architecture of reality. String theory invites us to imagine extra dimensions, beyond the up-down, left-right, forward-back we know. These dimensions could be curled tightly into tiny shapes at every point in space, like microscopic hallways folded inside the fabric of reality. We cannot see them, but strings can vibrate inside them, creating new behaviors, new particles, new laws. It is a universe more intricate than our senses can reveal. But string theory does not stop at dimensions. It suggests that the forces of nature, gravity, electromagnetism, nuclear forces, are not separate by design. They are born from the same vibrating structure. Physics becomes a single song played in different octaves, a unification that Einstein spent his final decades searching for. In the 1980s, physicists discovered that string theory was not one theory, but many, 5 major versions, each with its own structure. At first, this was unsettling. Why would the universe need multiple blueprints? What rule selects just one? Then, a breakthrough arrived. These theories were not separate. They were reflections of one deeper truth, connected by transformations called dualities. What changes in one theory appears in another as a new dimension or a new symmetry. Like turning a kaleidoscope to see the same pattern from a different angle, string theory revealed itself as a single elegant framework. And hidden at the center of this realization emerged something larger, M theory, a proposal that strings might be just slices of higher dimensional objects called brains. Entire universes could be brains, vast membranes floating in a larger space, occasionally brushing against one another. When brains collide, some theorists believe a Big Bang can occur. The birth of a cosmos could be the gentle kiss of 2 floating worlds. Look around your room. The air between you and the walls might contain dimensions too tiny to see. Every atom may hold tunnels into hidden spaces. Reality could be far richer than what your senses allow you to feel. But string theory also teaches humility. Despite its beauty, its symmetry, its ability to unify forces, evidence remains just beyond our reach. The scales involved are so small, the energies required so immense, that direct tests remain impossible with present technology. For now, string theory is not a confirmed truth. It is a possibility shaped by mathematics. But mathematics has guided us before. Einstein's equations predicted gravitational waves long before we could hear them. Quantum theory predicted antimatter decades before we found it streaking through space. Perhaps strings are waiting to be discovered the same way. First believed, then measured. Even without proof, string theory offers a poetic answer to a fundamental question. Why can particles transform? Why do forces unify at high energies? Why is spacetime flexible enough to bend? Because everything we know is a vibration of something deeper. In this picture, the Planck scale becomes the natural unit of reality, the length of a string, the beat of existence. We do not approach chaos there. We approach origin. Quantum foam becomes the dance floor, gravitons become the rhythm, spacetime becomes the music. And suddenly, gravity doesn't need adjusting to fit into quantum physics. It starts as quantum physics. If strings are real, then the universe isn't random structure. It is composed, deliberate, resonant. Like an orchestra that existed before ears to listen or minds to wonder, the cosmos began playing a song long before life arrived to hear it. As you breathe, every atom in your body vibrates, not metaphorically, but physically, each one performing its ancient notes. You are a chord assembled by cosmic harmony, a structure built from music older than stars. Perhaps that is why humans seek patterns, why rhythm comforts us, why harmony feels like home. If the universe is music, then we are shaped from sound. As we drift deeper into this night, one thought remains gently bright. Maybe gravity isn't a puzzle missing pieces. Maybe gravity is the first note in a symphony we are only beginning to understand. And if strings reveal the architecture of the cosmos, then another theory must explain what lies at the intersections of these strings, how they weave loops into geometry itself. Which leads us to our next question. If space is built from something discrete, tiny loops or nodes stitched into existence, could reality be a fabric not woven by strings, but knotted into place? In the next chapter, we explore that vision, a world of loops instead of waves, where space itself becomes quantized and gravity emerges from the architecture of existence. Part 9. Loop quantum gravity, space made of atoms. Another view says, space-time is not smooth at all. It is granular, woven from tiny loops like threads in a fabric. In this model, area and volume come in discrete packets, space is pixelated, and gravity is the architecture of those pixels interacting. This idea is called loop quantum gravity. It seeks to bring Einstein and the quantum world together by changing the very foundation of what we think space is. Instead of a continuous fabric that bends, loop quantum gravity suggests that space-time is built from individual units, atoms of space itself. These atoms are unimaginably small, so small that our most powerful microscopes cannot reveal them, so small that light itself is far too coarse to trace their boundaries. Each loop is a tiny ring of geometry, like a strand of thread, and just as threads can be woven into cloth, these loops interconnect, forming a vast network. Physicists call this network a spin network, a structure where every connection, every knot, every intersection encodes information about the shape and curvature of space. In this picture, distance is not a backdrop, it is a property. Area is not empty, it is counted. Volume is not continuous, it is built from quanta. If you were to zoom in far enough, the illusion of smoothness would dissolve into something more like a lattice. Every corner of spacetime would be a meeting point of loops, subtle and intricate. The geometry of the universe becomes a tapestry. And gravity? Gravity becomes the rules that determine how this tapestry changes. Traditional general relativity demands a smooth fabric, stretching and curving like a sheet of rubber. Loop quantum gravity replaces that with a dynamic network. Edges lengthen or shorten, nodes shift, new connections appear. These changes produce what we perceive as gravity. In one sense, loop quantum gravity is less about force and more about form. The universe becomes a living structure, constantly rearranging itself at the smallest scales. Space is not a stage, it is a participant. A remarkable property emerges from this model. Singularities disappear. In classical physics, a black hole's center collapses to a point of infinite density. The Big Bang originates from a similar singularity, an infinitely small, infinitely dense moment. But loop quantum gravity suggests that spacetime cannot compress beyond its smallest loops. There are no infinities allowed. The loops push back. This means black holes may contain no actual point of collapse. The Big Bang may have been a bounce from a prior universe. Spacetime has resilience, like a woven cloth that refuses to tear. The universe may have structure even in its darkest cores. Another beautiful consequence arises from this granular nature. Space and time might emerge from these loops. Time itself could be a sequence of changes in the network. Each shift, a node rearranging, a loop splitting, becomes the next moment. The ticking of the universe comes from geometry evolving in discrete steps. There is no continuous river of time, only frames of change played quickly enough that they blur together. Like a movie, reality is a series of snapshots. Loop quantum gravity also offers a solution to the mysterious entropy of black holes. Stephen Hawking showed that black holes have entropy proportional to the area of their horizons. In loop quantum gravity, that area is made of tiny tiles, each with a specific size. The entropy becomes simply the number of ways these tiles can be arranged. The mystery becomes a count. It all fits as though the universe has been waiting for us to see this structure. What makes this theory so compelling is its humility. It does not add new particles or dimensions. It simply changes our understanding of what space already is. But there is a challenge. How do we test something so small? The Planck scale, where these loops live, is far beyond the reach of current experiments. We cannot poke these threads directly. Instead, physicists search for indirect clues. Ripples in the early universe, slight variations in high-energy cosmic rays, deviations in gravitational wave patterns, quantum corrections near black holes. If any of these signatures match loop quantum gravity predictions, we would finally have evidence that spacetime has a texture. This shift in thinking has deep philosophical implications too. If space and time are not continuous, then motion is not smooth. A falling apple does not glide along a curve. It hops from loop to loop. Light does not travel in a single straight beam. It steps across nodes of geometry. The universe is not a canvas. It is a stitching. And we are stitched into it. Every structure you know, your chair, your heartbeat, your drifting breath, is tied into a vast network of quantum geometry. Your atoms occupy nodes within that network. The space between your thoughts is built from the same threads as galaxies, and in every moment, the tapestry rearranges. One quiet rearrangement at a time, time itself flows forward. Loop quantum gravity does something profound for our story. It suggests that unification does not require new realms or extra dimensions. Instead, it asks us to see the familiar differently. Gravity is not a separate force. Space is not empty. Time is not smooth. Even nothingness is filled with structure. If strings are musical notes, then loops are threads, woven into the backdrop that sound vibrates through. Both pictures, strings, and loops may be different attempts to describe the same truth from different angles. This harmony hints that the ultimate answer lies deeper still, at the intersection of physics and information, at the boundary between geometry and the quantum world, at the place where entanglement might be space-time. As you lie here now, wrapped in calm and quiet, the loops beneath you vibrate invisibly, creating the solidity you trust. Their intricate network makes room for stars to shine, planets to orbit, and consciousness to wonder why. Quantum gravity may not be the final chapter of physics, but it is a chapter that brings two worlds closer together, the infinitely large and the infinitely small, the smooth and the granular, the cosmos and the human mind. As we prepare to drift deeper into this quiet exploration, a question gently arises. If space and time are built from these tiny loops, what about time itself? Can time also be quantized, not a flow, but a pulse? In the next chapter, we explore the possibility that time, your time, cosmic time, is not continuous at all, but a sequence of moments stitched together by the quantum heartbeat of the universe. Part 10. Time may not be what we think. If space-time has structure, time might too. It might tick in tiny increments, moments too small to sense but real enough to reshape physics. At the Planck scale, time itself could be quantized, turning every second into a lattice of discrete events. We experience time as a smooth river. It flows forward endlessly, carrying us from one moment to the next. We cannot pause it, step out of it, or reverse its motion. Our every memory, every expectation rests upon the belief that time is continuous and unbroken. But in the quantum world, continuity is rarely real. Perhaps time does not flow like water. Perhaps it advances like footsteps. The smallest unit of time that physics can describe is called the Planck time, about 5:39:10:44 seconds. It is the span of time it takes light, the fastest messenger in the universe, to travel one Planck length. Shorter than that, the very notion of before and after begins to lose meaning. Events cannot be distinguished. For time to tick faster would be like trying to divide a single heartbeat into infinity, something the universe refuses to allow. Time, like space, may have a minimum grain. If that's true, the flow you feel is an illusion created by billions of these tiny units playing in sequence like frames of a film. The frames appear to blur, but beneath the illusion, the world changes in discrete jumps. Existence is not continuous, it is updated. Just as matter and energy behave in quantum steps, time might reveal its own quantized nature only at scales far too small for human senses. Your heartbeat, the rhythm of your life, is slow compared to time's invisible metronome. If we could zoom into a single instant, we might see that time is not a line, but a staircase. Each step, one Planck of duration longer, carries the universe forward. This idea changes everything we thought we knew, because if time is built from discrete moments, then motion becomes a sequence of stops and starts. Change itself becomes pixelated. Even the evolution of the cosmos must be counted in tiny ticks. What causes one moment to follow the next? Quantum physics suggests that time might not exist unless things change. If the universe were perfectly still, no particles shifting, no waves interfering, time could vanish entirely. There would be existence without motion, without sequence, without experience. A universe frozen not in place, but in meaning. In this view, time is what change looks like. In deep space, far from planets or heat, a lonely photon drifts silently. To that photon, traveling at the speed of light, time does not pass at all. Its journey, whether 1 meter or a billion light years, is experienced as the same. Motion without time, distance without duration, at light speed now becomes forever. Gravity itself changes time's tempo. Near massive bodies, stars, black holes, time stretches. Clocks slow, seconds lengthen. Gravity presses time downward, as though weight could bend minutes the way it bends space. High above Earth's surface, satellites age slightly faster than the people below. The universe does not share a single clock. Time is personal. This relativity suggests that time may not be a universal backdrop. It may be something that arises locally, woven into each region of space by mass, energy, and quantum structure. If gravity strengthens somewhere, time lingers. If motion accelerates, time shrinks. Every observer builds their own timeline from their own environment. Your past and future are stitched according to where you are, how fast you move, and how gravity holds you. But beneath all these stretched and shrunk experiences, a deeper question rises. If time can change its speed, does it truly flow? Or is it something we create to measure change? Einstein himself wondered whether time is simply another dimension, no more dynamic than length or width. Its flow an illusion created by consciousness moving along space-time. In this perspective, every moment that ever happens already exists. The entire history of the cosmos laid out like a painting, permanent and complete. We do not watch time flow. We trace a path through what is already there. A static universe, motion becomes perspective. Yet, quantum mechanics disagrees. Quantum particles behave as though time is not simply a coordinate, it is a process. Without time, probabilities cannot evolve. Without change, uncertainty cannot resolve into outcomes. Time must exist for quantum mechanics to work at all. Two realities again, relativity and quantum physics, pulling apart. This conflict invites a stunning possibility. Time might be emergent. It may arise from deeper phenomena, from the way particles entangle, from the way information spreads, from the way the universe remembers. Some physicists believe time may come from entropy, the movement from order to disorder. The arrow of time might simply reflect the universe's tendency to scatter energy. Eggs break, stars burn fuel, memories fade. All are signs that the cosmic deck shuffles in only one direction. But what if that direction changes? If the universe is cyclic, expanding and contracting in endless bounces, then time might reverse during collapse. The arrow could flip. Future might become past. Meaning might shift its orientation. We have never witnessed such reversal, but time has a history longer than our perspective. Imagine if before the Big Bang, time flowed backward. Imagine if every moment in that prior phase is connected to ours. Imagine if time is a loop, not a line. Loop quantum gravity reinforces this idea. If space is made of loops that can stretch and reconnect, time might vanish in regions where the loops break, only to re-emerge when the network stabilizes. There could be places, perhaps inside black holes, where time dissolves completely. A silence between ticks. And if time has silence at the smallest scales, then perhaps consciousness uses those silences to dream, to imagine, to wonder. Our thoughts unfold in rhythms that feel fluid, but deep down may be quantized. Our minds might already be synchronized with the quantum clock of the cosmos. Every heartbeat becomes a reminder. You are moving through time, but time is also being created beneath you. We do not merely travel through existence, we participate in its formation. So what is time? A dimension, a sequence, a measurement, a memory, or a property of matter interacting with itself? Geometry changing, information unfolding? Whatever time truly is, one thing remains certain. Its mystery is not a threat to understanding. It is an invitation to deeper wonder. And one question remains softly glowing as we prepare for the next descent into quantum gravity. If time flickers in discrete steps at the smallest scale, could the force binding those steps together be the same invisible network that gives rise to gravity? In the next chapter, we turn to a deeper connection, one that hints that gravity and entanglement may be two reflections of the same quiet truth. The universe stays whole because everything is connected. Part 11. Gravity and entanglement, a hidden link. Quantum particles can become entangled, connected instantly across the cosmos. Some scientists believe spacetime curvature might emerge from these invisible bonds. In this picture, gravity is not a force. It is a consequence of information being shared. Entanglement is one of the strangest discoveries in physics. When two particles become entangled, they no longer behave as separate objects. Measure one, and the other responds, even if they are light years apart. They act as though distance does not exist, as though the universe has tied them together with a thread that no amount of space can sever. Einstein called this spooky action at a distance, believing nature must be hiding a deeper explanation. But decades of experiments have shown that entanglement is real. It is not a trick. It is not a glitch. It is a feature of reality more fundamental than space and time. In the quantum world, connection is more important than location. This realization inspired a bold idea. Maybe space-time itself is made from entanglement. Imagine the universe as a vast network of relationships. Every atom, every particle, every photon is a node. The edges connecting them are entanglement links, information shared between objects that define their relationship. If many particles become strongly entangled, the network grows dense, the structure becomes rigid, distances gain meaning, geometry emerges, gravity emerges. In this view, the curvature of spacetime, the bending that makes planets orbit and shapes the paths of light, is not fundamental. It is the visible consequence of countless quantum relationships holding matter together. Gravity is not a force pulling things. It is the geometry created by entanglement. To slip deeper into this idea, imagine pulling apart two entangled particles. They resist separation, not with physical tension, but with a demand to remain correlated. That demand could be what we perceive as gravitational attraction, a manifestation of the universe trying to maintain its connectivity. The more matter you gather in one place, planets, stars, galaxies, the more entanglement lines weave around them. The geometry distorts. Space-time bends inward. Objects fall toward the center not because of a force, but because the network guides them along the most connected path. Gravity becomes information. This view is supported by a remarkable concept known as the entanglement entropy of a region of space. A black hole's entropy, its measure of disorder, is proportional not to its volume, but to the area of its event horizon. Information, it seems, is stored on a surface, not inside. This discovery gave birth to the holographic principle. A three-dimensional universe could be encoded on a two-dimensional boundary. The cosmos might be a hologram. Depth could be a useful illusion. If space is a hologram, entanglement is the glue. Without it, the image collapses, the illusion dissolves. Reality loses its ability to hold shape. One startling experiment helps reveal this truth. When researchers simulate entanglement patterns on a computer, they find that the resulting geometry automatically resembles curved spacetime. Even gravity-like behavior appears. Without inputting Einstein's equations, without telling the system what gravity should do, simply from the pattern of information sharing. This suggests something profound. Einstein's curvature may be the shadow of a deeper quantum structure. Gravity becomes the emergent music from an orchestra of entanglements. If a region of space loses entanglement, if information threads are cut, space itself may tear. A black hole might represent such a tear. a place where entanglement ends abruptly, creating a boundary. Inside that boundary lies a region disconnected from the rest of the universe. Space, in a meaningful way, ceases. This leads to a revolutionary idea about the structure of reality. Spacetime is woven from entanglement. Remove entanglement, and spacetime unravels. This helps explain why black holes are so special. They compress matter so tightly that quantum states become maximally entangled. Their horizons mark the limits of information exchange. Gravity outside the black hole behaves normally, but inside, the network might break completely. A singularity may not be a location, but an emptiness where connectivity is lost. Even more astonishing possibilities unfold. Wormholes might form when entangled particles link distant regions. The expansion of the universe could reflect networks dilating. Dark energy might emerge from information stretching space apart. Cosmic structure may be the geometry of entanglement itself. Every motion, every orbit, every fall might be a whisper from a hidden network reminding matter how to remain connected. You are held to Earth not by a force from below, but by invisible relationships that bind you to this planet, and this planet to the sun, and the sun to the galaxy, and the galaxy to every star that sparkles in the night. Connection shapes motion. Motion shapes time. Time shapes experience. Even consciousness might be part of this story. The neurons in your brain communicate through electrical and chemical signals, but quantum theories suggest that entanglement may subtly influence these processes. Your awareness may be a product of connectivity on scales both large and small. Your thoughts could be woven into the same informational tapestry as galaxies. As you lie still, atoms within you are entangled with atoms that once drifted in ancient stars. You are connected to the cosmos not metaphorically, but physically, and gravity is the expression of that connection. This idea brings a profound emotional symmetry to science. We fall toward each other because the universe will not allow us to be separate. The strength of gravity mirrors the strength of entanglement. When matter spreads apart, connections weaken. The geometry relaxes, space expands gently outward. The cosmos grows. When matter gathers tightly, connections intensify. Geometry buckles inward. Space closes around mass. The universe breathes through entanglement. As we move deeper into this quiet understanding, a final question emerges. If gravity comes from quantum information, what larger message does the universe hold? Where is information stored? How is it exchanged? And what does the cosmos remember? The answers lie in the most ambitious theories of all, where space-time becomes a projection and reality becomes a computation. In the next chapter, we explore the possibility that the universe itself is encoded like a hologram, and gravity is simply the shape that information takes when it becomes real. Part 12. Holographic Universes. What if gravity is an illusion? Some theories suggest the entire three-dimensional universe may be encoded on a distant surface, like a hologram. Every curve of gravity, every black hole, every galaxy, projected from information stored on a cosmic boundary. This idea is called the holographic principle, and it arose from one of physics' most stubborn paradoxes, the black hole information problem. As black holes absorb matter, their surface area increases, not their volume. Their entropy, their information content, scales with that area. It's as if all the information about everything that falls in is written on the horizon, not hidden inside. From that strange clue came a breathtaking thought. Perhaps all of reality works this way. In a hologram, a three-dimensional image emerges from a two-dimensional pattern. The depth your eyes see is an illusion created by the arrangement of light on a flat surface. The holographic principle stretches this concept to the largest stage possible. The universe might appear three-dimensional, but its true description might live on a cosmic boundary far away from everything we see. What feels like space inside, air around you, stars across the sky, could be the projection of information stored on that boundary. The gravity we experience might not be fundamental, but the echo of encoded structure. Gravity becomes the Earth's shadow in the language of information. Imagine standing in a room with walls that record everything inside. You move your hand, and the wall computes the change. That calculation then creates the sensation of motion, of force, of space. Your experience is real, but the description is stored elsewhere. If this sounds like science fiction, it isn't. It is science from the work of Stephen Hawking, Gerard 't Hooft, Leonard Susskind, and many others, born from equations, symmetries, and the refusal to accept paradox. In the holographic picture, information is the true substance of reality. Mass, energy, space, and motion are expressions of how information is arranged and evolves. Gravity emerges from the density of information, how tightly bits of reality are packed in relation to one another. In regions where the hologram is densely encoded, space-time curves inward. Where information spreads thinly, space-time relaxes outward. Gravity becomes information geometry. This description solves another puzzle: why gravity grows stronger near massive objects. Their information is more concentrated. The projection becomes more curved. Imagine the boundary of the universe as the ultimate hard drive. Every star, every particle, every heartbeat stored pixel by pixel on its surface. Our three-dimensional world becomes the performance of that stored data. We are walking through a projection that feels solid, yet may be written on a distant horizon. One of the most remarkable examples of a holographic universe is a model known as AD-CFT correspondence, which connects a universe with gravity, AD-ES space, and a universe without gravity, a conformal field theory on its boundary. Two entirely different theories describe the same reality. One includes curved space-time. The other, flat, no gravity at all, encodes everything. It's as if the universe offers two opposite translations of the same story. On the boundary, pure information. Inside, the lived experience of space and gravity. This profound duality suggests that gravity isn't the foundation, but a convenient illusion created by information. And this changes the questions we ask about existence. If the universe is holographic, where is the projector? Where is the screen? What lies beyond the boundary? Some physicists propose the boundary is the edge of the observable universe, the cosmic horizon created by the speed of light and the expansion of space. Others think the boundary might be mathematical, not a physical surface, but a structure describing all possible states, whatever the answer. This view brings gravity, quantum mechanics, and thermodynamics into alignment. The three great languages of physics begin to speak the same truth. Information is conserved. Information creates geometry. Geometry shapes motion. You fall to the ground not because Earth pulls you, but because the hologram bends the path beneath you to maintain consistency in its encoded story. Even consciousness may be part of this projection. Memories become data. Perception becomes interpretation. Self becomes a pattern written into the boundary and rendered into experience. This idea can feel unsettling, as though life is a shadow rather than a substance. But shadows still reveal truth, and projections can be beautiful. Existence does not require fundamental solidity, only consistent connection. The holographic principle does not diminish reality, it deepens it. We are participants in an encoded cosmos, not because we are unreal, but because the universe expresses itself through layers of meaning. Night sky above you, starlight traveling for billions of years. All of it might be a reflection of information whispered from the furthest edges of space-time. And this whisper is not static. The boundary evolves, the universe expands. Some theorists even believe the Big Bang was a release of boundary information inward, a sudden projection of a new world. As space stretches, new holographic pixels emerge, filling the cosmos with possibility. The deep connection between entanglement and geometry helps reveal how the hologram holds together. When two regions of the universe share information, entanglement rises. Where entanglement grows, space-time becomes more coherent, gravity becomes stronger. Your existence depends on relationships woven through information and projected into form. When relationships break, at the edge of a black hole, space-time tears. Gravity collapses. Information must find a new path. This is why the ET Holographic principle feels like destiny in our journey toward quantum gravity. It unifies the geometry of Einstein, the uncertainty of quantum physics, and the structure of thermodynamics. Three great puzzles joining into one quiet truth. Reality is information becoming experience. So this leaves one last question for this calm chapter of discovery. If the universe is a hologram, a projection of quantum data, what creates the data itself? What engine computes the unfolding story of existence? What law selects this universe out of all possible ones? What deeper logic breathes time, motion, and meaning into information? As we drift deeper into this silent night of thought, our journey continues to the largest scale of all, where the universe itself becomes a quantum object and the future and past merge into one expanding possibility. In the next chapter, we ask a profound question. What does quantum gravity predict about the birth and fate of everything we know? Part 13. Experiments in a world too small to touch. Testing quantum gravity is one of the hardest challenges in science. We cannot build microscopes small enough, nor accelerators powerful enough. Instead, we look to the skies, to black holes, neutron stars, and the earliest light of the cosmos, to see tiny clues magnified by extreme environments. Gravity becomes quantum only at scales smaller than anything we can physically explore. A proton is enormous compared to those depths. Even our most powerful particle accelerator, the Large Hadron Collider, barely scratches the outer shell of this hidden realm. If the Planck scale is the basement of reality, we are still wandering somewhere on the roof. So instead of digging inward, physicists look outward, into the massive, into the violent, into the cosmic. The universe is the only laboratory large enough to reveal the whisper of quantum gravity. Every black hole merger, every star's collapse, every flicker in the early universe becomes an experiment we simply happen to arrive in time to witness. We listen for messages carried across billions of years, messages written in waves of spacetime and in the oldest light that still roams freely. The first of these new tools is gravitational waves. When black holes collide, the fabric of spacetime ripples outward. These waves change distances by amounts so tiny we measure them with beams of light bouncing between mirrors miles apart, detecting distortions smaller than a proton's width. When LIGO first heard a gravitational wave in 2015, it was the universe speaking to us through its most primal vibrations. Two black holes spiraling into one another, a moment of pure gravity, told us that spacetime is dynamic. It can stretch, it can ring like a bell. But beyond that first discovery lies a deeper hope. If we detect enough gravitational waves with enough precision, we might see tiny quantum irregularities, subtle cracks in Einstein's smooth description. Small deviations from expected wave patterns could reveal granularity in spacetime itself. Every wave becomes a probe into the Planck-sized depths we cannot reach. There are other cosmic messengers too. Neutron stars, dense remnants of collapsed suns, hold matter crushed to its extreme limits. They spin rapidly, beam light like lighthouses, and sometimes merge in explosive bursts that forge gold and heavier elements. When such titanic events occur, they may generate gravitational waves and high-energy particles simultaneously. Comparing their arrival times allows physicists to look for something astonishing. Do gravitons, if they exist, travel differently from photons? If gravity has a quantum structure hidden inside, the signatures might appear when signals race across billions of light years. A difference in arrival by even the tiniest fraction of a second could reveal how spacetime fluctuates in its deepest layers. The universe becomes a stopwatch for testing ideas that Earth alone cannot. Another window into quantum gravity lies in the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light has traveled almost unchanged for 13.8 billion years. It carries memories of a time when the universe was dense, hot, and governed by quantum fluctuations stretched to cosmic scale by inflation. If spacetime behaved differently in those early instants, if time was discrete, if space was granular, tiny imprints could remain in the texture of that background glow. Subtle patterns in polarization, temperature, and distribution might reveal how gravity behaved when everything was new. The first moments of existence may hold the blueprint physics still seeks. We also search in unexpected places, in the behavior of high-energy particles called gamma rays. These particles travel through the universe at nearly the speed of light. If spacetime is quantized, different energies might move slightly differently, arriving from distant galaxies a bit out of sync. This time lag could expose the foamy nature of spacetime Wheeler envisioned. Even tiny discrepancies become golden threads to follow. Every anomaly matters, every unrealized detail might be a doorway. But the greatest challenges do not only come from observation, they also come from interpretation. The data we gather from cosmic laboratories can be sparse, noisy, and ambiguous. We often cannot repeat the same event with different variables, as we would in a traditional lab. We get one glimpse, one burst, one collision, and then we wait for the universe to speak again. Quantum gravity hides behind the limits of measurement. It thrives in silence. It resists certainty. Even so, human curiosity pushes forward. New instruments rise. LISA, a space-based gravitational wave observatory. Extremely large telescopes peering deeper into the cosmos. IceCube, catching neutrinos from violent cosmic engines. Quantum sensors measuring distances. At unprecedented precision, we are building ears tuned to whispers. Future colliders, far beyond Earth's scale, are also being imagined. Vast rings in space, particle accelerators driven by plasma waves, technologies that exist today only as dreams may one day unlock the threshold we seek. Yet something remarkable is already happening. Theories once thought separate are beginning to rhyme, from string theory's vibrating geometry to loop quantum gravity's woven space to entangled spacetime and holographic universes. Each suggests that gravity and quantum mechanics are not incompatible foes, but partners describing different sides of a hidden structure. Experiments may not yet reveal quantum gravity outright, but they are narrowing the search, sharpening the picture, guiding intuition. Even failures to find certain effects teach us what the universe is not. Each unanswered question becomes a corridor leading to a quieter truth. And here's a gentle realization. We study quantum gravity not only to solve physics, but to understand our place between the cosmic and the microscopic. We live at the crossroads of two great worlds, the quantum dance inside our atoms and the gravitational choreography of Earth circling the sun. Where those worlds meet, reality becomes more mysterious than either alone. As you rest, your body is held by gravity, calm, familiar, steady. Yet within you, electrons move through quantum states without regard for gravity's pull. The universe uses different rules for the realms that shape you, and somewhere in the gulf between those rules lies the secret of existence. Every new observation brings us one quiet step closer. Every signal from deep space is a gift from the unseen. Every challenge strengthens our resolve to listen deeper still. And so, surrounded by starlight and gentle dark, we follow the evidence wherever it leads, toward a theory that unites motion and uncertainty, toward the moment when physics becomes whole. But before we arrive, there is one more question to consider. If gravity becomes quantum only at extreme scales, why should it matter to us here, in this quiet moment? Because quantum gravity may be the reason the universe is stable, the reason stars form slowly enough for life to emerge, the reason time flows in harmony with consciousness. Because the nature of spacetime shapes the nature of everything. In the next chapter, we finally bring every thread together to ask what quantum gravity truly tells us about the universe we call home and the future of the laws that hold it together. Part 14. When we finally detect a graviton, physicists dream of the moment when a gravitational wave detector hears a single particle's whisper. A graviton. That quiet signal could bridge Einstein's smooth spacetime with the quantum world. In that instant, two great theories would finally meet. Imagine the celebration that followed the first detection of gravitational waves. In 2015, ripples in spacetime from black holes colliding light years away. It was a triumph, a confirmation of Einstein's vision. but those waves still spoke the language of large-scale gravity. They bent space-time smoothly, predictably, exactly as relativity tells us they should. A graviton would be different. It would speak quantum. Gravitons would represent the smallest possible unit of gravitational influence, a single vibration of space-time, where gravitational waves are ocean-sized swells rolling across the universe. A graviton is a single droplet, a particle so subtle that it interacts with matter almost not at all. It passes through stars, planets, detectors, unnoticed. Catching one would mean listening not to the cosmic surf, but to the faintest trickle of water in a silent sea. Even if a graviton hit a detector head-on, the interaction would be so gentle that it could take longer than the age of the universe to happen once. The difficulty is staggering. It requires a patience beyond lifetimes, a technology beyond our era. And yet, scientists persist, not out of stubbornness, but hope. Because a graviton, once detected, would be proof that gravity has a quantum heartbeat. Every force we know obeys this rule. Electromagnetism, carried by photons. The strong force, gluons. The weak force, W and Z bosons. But gravity remains alone, fundamental, unquantized, a force without a particle, until a graviton appears. To imagine that moment, let's think about what would truly happen. In current gravitational wave detectors, enormous mirrors hang suspended kilometers apart, measuring the tiniest tremors in the fabric of space. But these machines are designed to hear choirs of gravitons, countless particles moving together as waves, not single notes. To detect one graviton, we will need a new kind of listener. Physicists imagine futuristic detectors, constructed of ultra-cold matter found only in collapsed stars, shielded from every vibration, every photon, every atom of air, possibly floating in space, far from cosmic noise, sensitive to the quantum flicker of geometry itself. These are not devices we can build yet. They are ideas waiting for technology to grow into them. But when that day comes, when one graviton lands, its arrival would be more than a detection. It would be a union. Einstein's curved spacetime would finally shake hands with quantum mechanics particles and probabilities. Smoothness and granularity would become one language. For the first time, gravity would be part of the quantum family. Yet there is another layer to this dream. Detecting a graviton isn't only a test of theory. It is a test of meaning. It would tell us whether the universe is built from discrete steps of existence, whether every gravitational interaction you have ever felt, from lifting your hand to Earth's orbit around the sun, has come from countless invisible exchanges. Every fall you've experienced, every breath held to the planet, every flow of tides and stars, all composed of tiny, unseen touches. A graviton detection would rewrite our understanding of presence itself. Gravity would no longer be a classical background. It would become part of the quantum conversation. It might explain why gravity is weak, if gravitons explore hidden dimensions, how information escapes black holes, what happens when space-time granulates at the Planck length, why the universe expanded from the Big Bang the way it did. The tiniest particle could solve the largest mysteries. Imagine the announcement, a quiet press conference, a team of researchers stepping to a microphone, an audience holding their breath. We have observed a signal consistent with the interaction of a single graviton. No fireworks, no shock waves, just a sentence. And yet, physics would cross a threshold it has pursued for a century. From that moment on, gravity would no longer be a mystery separate from the quantum world. It would be woven into the same tapestry. Relativity and quantum mechanics, once conflicting, once distant, would be partners again. The universe would look more unified, more whole, more elegant. But there is a deeper, quieter significance. Detecting a graviton would mean we have learned to listen to reality at its lowest volume. It would mean that beneath the roars of stars and galaxies, we have found the patience to hear a whisper, one that has always been speaking but never before heard. You are held to earth by an orchestra of silent particles. Your body rests in harmony with unseen geometry. Every step you take rearranges threads that stretch into the stars, and a graviton detection would prove that each of those threads has a quantum beginning. Gravity becomes not a force that presses downward, but a conversation that continues quietly around you at every moment of your life. Physicists call the search for gravitons the ultimate measurement because it would complete the map of fundamental forces, because it would close the deepest gap in our knowledge. But there's another reason too. It would prove that the universe is understandable, even at its most hidden scale, even in its most silent truths. The fact that we can even imagine detecting a graviton is a celebration of curiosity itself. Human minds, built from particles that once drifted in stars, are reaching down to the smallest secrets of existence and asking, how does gravity breathe? One day, perhaps soon, perhaps long after our age has passed, the graviton will no longer be a ghost. It will become a data point, a signal on a graph, a confirmation that reality is deeper and more connected than any single theory has yet been able to express. And on that day, a new physics will begin. Quantum gravity will not be speculation, it will be science. A doorway will open, not just to understanding the universe, but to understanding why the universe allows itself to be understood. As we drift forward, as we descend deeper into this quiet cosmic dream, the question lights gently ahead. After the graviton is found, what truths will become visible behind it? What shape will the completed picture of reality take? In the next chapter, we explore that final perspective, turning our gaze outward once more to the cosmos that gave birth to every question we ask and every answer we slowly uncover. Part 15. A universe built on uncertainty and curvature. Gravity becoming quantum doesn't destroy our understanding of the cosmos, it completes it. It reveals that certainty and uncertainty coexist, that the vast and the tiny are reflections of the same rule, and that the universe, from the first moment to your quiet breath tonight, is one continuous unfolding story. Everything we have explored, general relativity, quantum mechanics, gravitons, spacetime loops, holograms, entanglement, are not separate theories competing for truth. They are different chapters of the same book, each one describing reality at a different scale, each one illuminating something the others cannot. Relativity tells us how planets orbit, how space curves, how time slows. Quantum physics tells us how atoms dance, how probability rules, how existence flickers. Quantum gravity is the bridge between them. It does not choose sides, it listens to both and answers softly. It shows us a universe that is not purely smooth nor purely granular, but beautifully both. At human scales, you feel no quantum ticks of time. You see no vibrating strings, you sense no entanglement lines keeping you connected to stars. Yet all of those hidden behaviors shape the world you experience. The stability of atoms depends on quantization. The shape of galaxies depends on gravity. Your existence depends on both. The universe does not need you to see its rules for those rules to hold you gently. As scientists work to unify physics, they are discovering a deeper pattern. Certainty and uncertainty are not opposites, they are partners. General relativity gives certainty. A planet moves on a calculable path through curved spacetime. Quantum mechanics gives uncertainty. A particle's position remains a question until observed. Quantum gravity reveals how the two embrace. Paths curve, even in the quantum realm, and uncertainty shapes the structure of that curvature. Even the cosmos itself carries this dual nature. The universe expands predictably, steadily. Yet its earliest moments were driven by quantum randomness. Fluctuations smaller than atoms stretched into the arrangement of every galaxy we see today. Every star's position traces back to a probabilistic flicker in the first instant of existence. Uncertainty became the architecture of the night sky. And this matters deeply. Because if the universe had been perfectly smooth, perfectly symmetrical, perfectly predictable, nothing would have formed. No stars, no planets, no life, no quiet night to reflect upon. Imperfection is how structure begins. Even within you, the quantum world shapes biology in ways we are still learning, from the stability of your DNA to the chemistry of your thoughts. Yet gravity keeps you grounded, keeps your heart beating in rhythm with Earth's pull, keeps time flowing in one gentle direction. Two truths, one tiny, one grand, guiding the same life. Quantum gravity suggests we may one day understand the universe as a single, seamless whole. The smallest node in a spin network, the quietest note from a vibrating string, the faintest graviton drifting through space, all of them contribute to the geometry that shapes suns, galaxies, and the expansion of everything. We often imagine the universe as something separate from us, distant, unreachable, vast beyond comprehension. But the quantum and gravitational rules we study are not far away. They are here, in your atoms, in your weight upon the world, in every second you experience. The curvature of spacetime is the reason your feet feel the floor. The quantization of matter is the reason you do not fall through it. Every breath brings you closer to the fabric that holds you. In the quiet scale of a single cell, uncertainty reigns. In the cosmic scale of galaxy clusters, gravity shapes destiny. Together, they form a universe capable of both order and creativity. A universe stable enough to endure, yet flexible enough to evolve. Perhaps the most beautiful realization of quantum gravity is this: the universe does not exist in spite of uncertainty. It exists because of it. Curvature and unpredictability are the twin engines of creation. Smoothness gives form, randomness gives possibility. Your life, the improbable sequence of events that led to this very moment, was carved by both. Quantum gravity also changes how we think about beginnings and endings. If spacetime is quantized, the Big Bang may not have been a singularity, not an impossible point of infinite density, but a transition, a bounce, a new universe blossoming from a prior one, an ongoing cycle rather than a single spark. Even black holes, those dark mysteries of collapse, may not destroy information at all, but transform it. Death becomes a doorway, edges become origins, and if entanglement truly weaves spacetime, then the universe is fundamentally relational. Nothing exists alone. Everything exists through connection. You are linked to every particle around you. Every atom inside you remembers collisions in ancient stars. Every heartbeat echoes through the geometry beneath your feet. Quantum gravity reveals a deeper unity, not just of physics, but of existence. It tells us that the laws holding galaxies together are the same laws that guide electrons in their orbit. It says that the vast and the tiny speak the same language, a language we are only just beginning to translate. Even our limitations become part of the wonder. We are small beings trying to understand a boundless cosmos. And yet, we have already uncovered patterns written into reality from its first moment. The universe allows itself to be understood because understanding is woven into its structure. Information is preserved. Order emerges from chaos. Curvature is born from connection. Possibility rises from uncertainty. And we are here, not by accident, but because the rules of physics invite complexity to bloom. As you rest tonight, gravity cradles you gently. Quantum fields ripple invisibly within you. Time unfolds one moment at a time, according to principles older than stars. You are not separate from the cosmos. You are a piece of it, made of the same particles, following the same laws, moving to the same rhythm. In a quantum gravitational universe, nothing is isolated. Every atom touches the rest through silent curves. Every future grows from fluctuations that welcomed imperfection. The universe continues its story, and you are a chapter within it. So, breathe softly. Feel the weight that holds you. Feel the quiet motion of life in your veins. Feel the calm certainty that you belong here. The universe is vast, yet it has room for every detail, every uncertainty, every connection, every conscious moment of wonder. And as we near the end of this journey, one final step awaits. A gentle reflection on everything we have explored. Gravity's smooth embrace, quantum reality's flicker, and the unity waiting just beneath awareness. In the outro, we will close our eyes and rest in the knowledge that the universe is both mysterious and kind, and that every discovery brings us closer to understanding the quiet miracle of existence. The universe is not a puzzle to be solved in one night. It is a gentle invitation to wonder, to breathe, to listen. Tonight, we have drifted across the very fabric of existence, from the smooth curves of gravity to the restless flicker of the quantum world, and into the hidden scales where the two become one. We have followed gravity down to the Planck length, where space-time foams and trembles. We have imagined gravitons quietly carrying every fall. We have explored strings vibrating in unseen dimensions and loops that weave the architecture of space. We have felt time quantize into tiny instants and watched entanglement hold the cosmos together. We have seen black holes transform collapse into creation. We have watched information shape geometry in a universe that might be a hologram of itself. We have looked to distant collisions, ancient light, and silent waves rolling across the cosmos to catch whispers of quantum gravity arriving from the dawn of time. And through it all, one truth has remained: the universe is connected, in its laws, in its stories, in its quiet purpose. Your body rests here on Earth because gravity holds you in a cosmic embrace. Your atoms exist because the quantum world forms matter from possibility. Your time moves forward because space-time continues its silent unfolding. The cosmos is not separate from you. You are made of its rules. You are written into its fabric. As you drift into sleep, remember this: every star you've ever seen, every breath you've ever taken, every thought that rises and falls in your mind is part of the same continuous story, a symphony of curvature and uncertainty that has played for nearly 14 billion years. There is no need to understand everything tonight. There is only this moment, this gentle awareness that you are here, and the universe is here with you. Thank you for spending this quiet journey with me. If this calm space brought you peace, a gentle like, or a soft tap on subscribe, would mean more than you know. For now, let your thoughts slow. Let gravity cradle you. Let time soften and stretch. Let the universe keep unfolding as you rest in its endless glow. Good night, and may your dreams follow the quiet path where science becomes wonder and wonder becomes peace.